We're given an array of positive integers. Our goal is to find the second largest distinct number. Distinct means it must be different from the largest. If every number is the same or there's only one unique value, we return -1. Example 1, look at 12, 35, 1, 10, 34, 1. The largest number is 35. The next largest, that is different from 35, is 34. So the second largest distinct value is 34. Output is 34, and that's what we return. Example 2, the array is 10, 5, 10. The largest number is 10. We need the next largest value that's different from 10. That number is 5. So the second largest distinct element is 5. Output is 5, and that's what we return. Example 3, the array is 10, 10, 10. All numbers are equal, so there's only one unique value. That means there is no second largest distinct number. In this case, we return -1. Output is -1 because a second largest doesn't exist here. First, sort the array in non-decreasing order. That simply means arranging the numbers from smallest to largest, with equal values grouped together. Sorting gives us a clean order to work with, so later steps become easy. After this, the array is neatly organized and ready. Once sorting is done, the largest value sits at the very end of the array, at index n-1. You don't need to hunt around. Just look at the last position. That single spot holds the maximum element we will compare against in the next step. Now scan backward. Start at index n-2 and move left one slot at a time. Compare each number with the maximum at the end. The first value that is different from the maximum is your answer, the second largest distinct element. Stop as soon as you find it. If you reach the start without finding a smaller value, it means every element is equal to the maximum. There isn't a second largest distinct number in this array. In that case, return -1 to signal that no distinct second maximum exists. About time, sorting the array costs O of n log n. The backward scan can take up to O of n, but that doesn't change the big picture. Sorting dominates the runtime, so the total time complexity for this approach remains O of n log n. For space, we keep it tiny. We sort the array in place and use only a few constant size variables to scan and compare values. No extra arrays or data structures are needed, so the auxiliary space for this method is O of 1. Here's the plan. We scan the array 2 times. The first trip only notices the biggest number. The second trip looks again to find the next biggest, while ignoring that first value. With these 2 simple passes, we reliably get the second largest distinct element from the array. First pass is simple. Walk through the array once and track the largest value. Start with the first element or -infinity. For each number, if it's bigger than your current largest, update it. At the end of this pass, you know the array's maximum. Second pass time. Scan again, but skip any value equal to the maximum you found earlier. Among the remaining numbers, track the biggest one you see. Keep a single candidate and update it whenever you meet a larger number. That final candidate is the second largest distinct element. Edge case. If every element equals the maximum, there's no second distinct value. Maybe the array has one unique number, or it's all the same. In that situation, our second pass won't find a candidate, so we return -1 to signal no second largest. Cost check. 2 passes over n items gives linear time O of n. Space stays constant, O of 1, because we keep only a few counters. So this method is fast and lightweight. Scan twice, update variables, and you're done, without allocating extra structures. Here's the one-pass idea. Walk the array once while holding 2 numbers, largest and second largest. Start them at -1. For each value, we update these 2 on the fly. This keeps it simple and avoids a second sweep, all in a single pass. If the current number is greater than largest, first copy largest into second largest, then set largest to the current number. Think of it as shifting everything down by 1. This keeps the top 2 values correct as we continue scanning the array. If the number is smaller than largest, but bigger than second largest, update second largest to this value. We require strictly less than largest, so the second place is truly distinct. No other changes are needed, and we keep scanning forward with both values ready for the next comparison. After the single pass, return second largest. It holds the second biggest distinct value seen during the scan. We're done at this point because our two trackers have been updated on every step. Just output second largest as the final answer for the array. If no second distinct value ever appears, second largest stays at -1. That means all elements were equal, or there just weren't enough different numbers. In this case, we return -1, clearly signaling that a second largest distinct element does not exist in the array. The whole scan is linear time O(n) because we touch each element once. Space is constant O(1) since we only store largest and second largest. Compared to the two-pass approach, we compress the work into a single sweep without any extra memory or sorting.